Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to write equations of motion that describe an object that's moving along with constant acceleration. So what we're going to do is we're going to take a look at this car here, this animal right here, and I'm just making up values off the top of my head. We are going to assume it is 20 meters from the right of this coordinate system at t equals 0. We're going to assume it's moving to the right at 6 meters per second. And the driver is applying the gas, speeding the car up at about 4 meters per second. We are going to try to then calculate at what time will it take the car to reach 100 meters to the right. So first of all, when you're working any of these problems about motion, you want to make sure that your picture describes what's happening here. So in this case, we have this car that's speeding up. Now, this red dot here was put here to represent like where we're measuring to. So what I mean by that is like this is what we're calling x. And if the car were moving at constant velocity, then if I were to draw a motion diagram for the car, it might look something like this. The delta x's, the distance between these dots, would be the same. However, the car is speeding up at about 4 meters per second. So as time goes on, the delta x's would get higher and higher and higher because the velocity of the car, right, which might be 6 meters per second in this picture, is going to be a little more and a little more and so forth. So these are velocity vectors. Okay, so now my picture graphically shows that that car is speeding up. All right, next. Typically, if you sketch what I call velocity graph, that is a great place to start for analyzing the motion of a particle or an object. So I'm going to go ahead and do that. There we go. All right, and this doesn't have to be perfect, just a rough sketch of what's going on. So at t equals 0, this car is moving at 6 meters per second. I'm just going to put that point here, right? 6 meters per second. Where you put this up and down doesn't really matter. Just understand that now I've kind of set a scale. Since I put 6 there, 3 would be roughly here, 12 would be roughly here, and so forth. And the velocity is increasing with time. So a second later, I would expect to be going 10 meters per second. And then a second after that, a little faster. Now what we're going to do is we're going to kind of let this float. That's what I like to call that. We're just going to call that t. Now I've already built in an assumption here by drawing that linear. We are assuming that this is not changing. That's called a constant acceleration assumption. It's a pretty common assumption when studying the motion of an object. All right. Now we want to be able to write a couple of equations for the car. One to describe its velocity against time, and the other its position, its x coordinate against time. So this is function notation, v of t and x of t. That's what we're looking for. Now I've made a couple of videos on how to do that. The velocity function, again, it's linear. The intercept is the 6 meters per second. I'm going to leave the units out of this. And then the slope is the acceleration, and then times time. And I'm just going to put NCU for note consistent units. The units are consistent in this problem. So there is our linear velocity function that we expect when our acceleration is constant. Now, again, what that represents, this is a really important thing. This equation represents this distance on the graph. All right, next one. So to get our delta x, what we're going to do is we're going to write an equation using this area here. And again, that's a trapezoid. To find the area of a trapezoid, you take the left, which is this, right? 6 meters per second. Again, units are consistent. I'm not going to write them. Plus the right, that's this. And again, here's the kicker. Here's what gives people trouble. That's not a number, that's a function. We just use it anyway. 6 plus 4t, right? Then divide by 2. times the width of the trapezoid, which is that distance right there. So times t. And again, really important to realize, this is this function, which is this distance on the graph. All right, next line. So the delta x is equal to x final minus x initial. And we look right here. Remember, the x initial is 20 meters. Equals. Now, as we look at this, let's see, 6 plus 6 is 12. Divide by 2 is 6 times t, 6t. And then this product right here is 4t squared over 2, 2t squared. So plus 2t squared. Now just move the 20 over to the right. So x equals 20 plus 6t plus 2t squared. There is our position function for the car. Okay, now, to answer our question, what is t when x equals 100 meters? So in our equation here, I'm just going to rewrite it now and put in 100 for x. 100 meters equals 20 plus 6t plus 2t squared. Again, the units are all consistent in this problem. And then what we would do is we would solve this for t. It's quadratic. So we probably would do something like this. That's from subtracting 100 from both sides. Now, I don't have a calculator on me, and this thing probably is not going to factor. Suppose we can do one more line. Let's see, everything's divisible by 2. It is very doubtful that this thing is going to factor, as I just made this problem up. The rest of this problem would be to solve this for t. And you would do so by applying the quadratic formula. The purpose of the video, though, was basically how to draw this to write this. So I'm going to go ahead and leave the solution of this thing there as an exercise to the reader. I hope that this helps. Have a great day.